Hello, my name is Nick Anderegg, and this is my talk, Oops, I Committed My Private Key, Automating Personal Security from Scratch with IoT and Infrastructure as Code. If you want to, you can find me on Twitter and GitHub as @NickAnderegg, and feel free to tweet me your questions or comments or feedback. The slides will be available on the GitHub repository on this slide as well. After the talk. So let's go ahead and get started. So I'll start by telling you a little bit about me and a little bit about the goal of this talk before we get started. So I'm not here on behalf of any company, as my former employer had some team restructuring about a month ago and I was unfortunately laid off. But by trade, I'm a developer and a developer advocate. And I like to describe myself as someone who specializes in being a generalist. So if you're hiring for any remote positions, definitely feel free to reach out to me. Note that I'm looking for permanently remote roles because I was remote before the pandemic and I want to stay remote after the pandemic. So there's the obligatory sales pitch for myself. And now we can get back to the parts of my biography that are actually relevant to the talk. So first and foremost, I'm a Python programmer, a DevOps advocate, and a tinkerer. And one of my favorite things in the world is building tools and automating complex workflows. And I love to dabble in IoT and information security. So this talk was an obvious conclusion of the intersection of those interests. As you'll learn from this talk, I have an addiction to Raspberry Pis and YubiKeys. Now, I feel like it's important for me to offer you this disclaimer at the top of my talk. As I'm just a tinkerer and a DevOps advocate more than anything, I want to clearly state right now, I'm not an expert in security or cryptography. I don't have formal training in InfoSec or cryptography. I have, however, done a lot of research on the topic for this project, and most of what is included in my talk is synthesized from what actual experts have to say. And that's to say, everything I say over the next half hour, 45 minutes could have gigantic security flaws. I don't think it does, but I would suggest you do your own research or consult an expert before you implement a system that has money riding on it. Don't sue me, please. So the project I'm going to present to you, I am missing a slide, I think. Yes, I am. All right, so the goal of this talk is to present a project that I built to automate security for myself, my personal projects, home automation projects, systems on networks that I manage for other people. And, what led me, you might be wondering what led me to create this project and give this talk that I'm giving right now. Well, as the title suggests, it was after I committed a private SSH key for the second time in 3 years. And although I have to admit that while this title is based on a true story, it's slightly clickbait because in both cases where I did commit the private key, they were disposable project-specific keys. Now, you see what I would do is I had this bash script that I would frequently use that I wrote that was called make SSH. What this script would do is it would take a host name that I was going to create, for which I was going to create the key. It would sign into my password manager, which was LastPass at the time. I now use 1Password. It would generate a new key and generate a passphrase for the private key file. It would add the passphrase to the password manager. It would add the actual SSH key to the SSH agent. It would add a backup of the key to the password manager, which I'm not quite sure what I was thinking there. That's not a good idea. But then it would add the new key to the SSH config file. Of course, after a while, I think most, if not all, SSH config files have a tendency to eventually become a giant mess when you have a bunch of different hosts with different situations that you need to connect to. And so for ephemeral projects, especially if I'm just experimenting with something or trying out a new tool, I don't necessarily want to have to deal with it. So in those cases, I would often just create an SSH key for specific use in that project. And I just store it right in the directory of, the Ansible project or whatever sort of project I was working on. And of course, that might mean that I have to do some extra configuration for the tool like Ansible to make it actually use that SSH key to connect to the server. But that I didn't mind that. It was easier than having a mess of an SSH config file. Of course, after a long, long period of time of working on that project, I might forget that the key was being stored in the project's directory and accidentally commit it. If I'm just experimenting and I don't really have an end goal in mind, I might have a whole bunch of files and I want to just have a checkpoint commit and save them all so that I can, branch and move on to a new project or move on to a new approach and save everything I have. And so then I commit the key by accident because I do a git add all and I push it up to the cloud, up to GitHub or whatever, wherever I'm putting it. And that's obviously less than optimal. So is there a better solution? There is, or this talk would be pretty pointless. So before I dive into it, I just want to tell you what the goal of this talk is. Whenever I originally pitched this talk, I was thinking of doing like a nitty gritty, like how-to type of thing. And, the solution I came up with is one that's really good for my specific use case. So I don't necessarily think that it would be of interest to everybody else to, give you step-by-step of how my project works. And so what I'm going for here is like a conceptual overview, a kind of talk that you can look at. And if you walk away at the end and you think, oh yeah, that's a good idea, then I think I'll have done my job. So let's dive in. So what are the goals of the project that this talk is about? The first is to prevent accidental data leaks. Basically avoid any sort of situation where the private key can accidentally be committed and tightly control access to the private data that's actually being stored in general. Like all my private data that I need to move between machines, need to use to access machines, passwords for accessing services from automated systems, things of that nature. I want to have it nice and controlled. I don't want to just throw passwords into text files. This isn't some completely impenetrable system. Have to reference the classic XKCD where, it's the crypto nerd's imagination that you can't crack the encryption because it's 4096-bit RSA, but, you drug someone and hit them with a $5 wrench, still just tell you the password. If you tell me you're going to drug me and hit me with a $5 wrench, I'll probably just tell you the password. It's not that important. The second goal is to make data access auditable. Basically, I want to be aware what's accessing the data so that I can be aware if there is any leak. Again, that makes me aware of any breaches or hacks. And of course, if you drug me and hit me with a $5 wrench, I'm going to be aware that you have my data. Next, I want to mitigate the effects of breaches so that if, for example, a key does leak, I don't really have to worry about it. The damage will be contained, or at least it will be minimized. And finally, I want to make everything reproducible. My dream technological setup would be like if, my apartment burned down, I can just pull down the Git repositories and, have everything set up exactly the way it was before. That's my dream goal of having everything reproducible. I love DevOps. So with these goals in mind, let's take a look at how we can do it. Let's start with the tools. So the first tool is Ansible. This is my preferred tool for configuration management and automation. It uses YAML-based playbooks to create idempotent configurations. And what that means is that if you specify that you want to have a certain file copied to a server, or you want to change a certain piece of configuration, it will check and see if that state already exists. And if it does, then it doesn't have to do anything. The playbooks you define are ones that define what the final result of the configuration should look like. And the fact that it uses rules and collections in a very modular way makes it easy to mix and match pieces to be able to configure things for new use cases. So how does this work towards the goals that we have in mind? It doesn't really necessarily help with preventing leaks or making access audible or mitigating breaches, but it does make deployments reproducible. If I define the final state that I want every single piece of hardware and software to be in, then obviously the build is reproducible. I can reproduce everything for which I configured using an Ansible playbook. The next tool is Packer from HashiCorp. This tool builds it's a tool for building machine images on various targets. For example, you can build AWS or DigitalOcean or whatever cloud provider machine images. You can build, as you can see in my example here, you can build VirtualBox images, Docker images, Parallels images, and there's actually a plugin that allows you to build images for a Raspberry Pi. So that makes builds extremely reproducible because you don't even have to rerun the build, you just have to redeploy the artifact. So again, this doesn't really help with the first three goals, but it is a huge step towards creating reproducible deployments. The next tool, which I'm sure we're all familiar with, is the Raspberry Pi. The reason I have an addiction to this inexpensive ARM-based single board computer is because it allows you to spread a lot of resources where you need them to be. A comparison I like is that the 12-core, 24-thread Ryzen 9 3900X desktop processor costs about $500 US. For that same price, you can get 14 Raspberry Pis that have 56 total cores and 14 gigs of RAM. It's really nice if you have a small application that you need to deploy a specific machine to, because you don't have to worry about balancing resources between all of the different things that might be running on a big server. If your specific application only requires 3 threads, a single Raspberry Pi provides more than enough. I'm actually using a Raspberry Pi to run a GPS-based NTP server. And, I have the niceness of the GPSD set at -20, but there's only like 3 threads running at any given time, so it doesn't actually really even matter. So how does this help us meet our goals? It doesn't really do anything to make access audible or mitigating breaches, but it does help with reproducible deployments. If we use Packer to build a machine image, we can just plug it into the Pi, it's ready to go. And this helps with leak prevention. Now you might be wondering how, and the answer is in the next tool, the Zimbit ZimKey. This is a $43 hardware security module for the Raspberry Pi. As you can see, it's outlined in blue in the picture of the Raspberry Pi. It just plugs into the header, and you can use a programmatic method of access to access the encryption hardware on the ZimKey and access the AES key that's baked into the hardware. It also comes with a real-time clock, random number generator. But the important thing here is the AES key that's baked into the hardware. Now this, whoops, wrong way. This doesn't really help us with auditing or reproducible deployments, but as I said before, it helps with leak prevention and it helps to mitigate breaches. Basically, when you pair a ZimKey with the Raspberry Pi, it becomes locked to that specific Raspberry Pi. Whenever it boots up, it has a system check that checks I believe it's the MAC address of the actual board itself, as well as the CCID of the micro SD card that you have plugged into it, and the serial number of the ZIM key. And if those three things aren't all in the same place, they aren't what the ZIM key expects, it won't boot up and it won't unlock the AES encryption engine. So this makes it, you can have this tiny little board that's extremely secure, effectively turning it into a hardware security module depending on what software you run on it. The software in question is Vault, another project by HashiCorp. This is secret management software. It has a CLI, HTTP APIs, and a number of clients that you can use to actually just access it over HTTPS. It allows tightly controlled identity-based access to secrets. So you define a role, and when that role is defined, any user that has a role will only be able to access the secrets that are allowed to be accessed by that identity. And we can use this for automation of key and certificate management across our infrastructure. And this helps us with a lot of our goals aside from reproducible deployments. It helps with the other three. It has built-in auditing mechanisms. It has leak prevention because it, is encryption software. So obviously that helps with that. And it helps us mitigate breaches in the particular setup we're going to use. If we have short-lived tokens and certificates, a breach isn't a big deal because if a certificate with a TTL of 24 hours is stolen, it's only usable for 24 hours, obviously. So how are we going to put this all together? What is the plan? Now, as you might have seen in the description of this talk, it's going to require a little bit of bootstrapping. But basically, we're going to be running a cluster of 3 Raspberry Pis that each have a ZIM key and are each running an instance of Vault. Now, before we dive into how that actually works, let's talk about some concepts of how Vault works itself. So each Vault has a seal. And the storage backend that Vault accesses to store your secrets and return data to you has a master key. The master key is encrypted while the Vault is sealed. And the unsealed keys are given to you using Shamir's secret sharing, that's a tongue twister for me, Shamir's secret sharing algorithm to split up the key data and either allow you to split it between multiple people or between multiple places, or however else you want to split it up. And a storage backend is what actually holds the encrypted data. The Vault server encrypts the data that you pass to it, and you can't get the encrypted data out of the storage backend without receiving it from the Vault server. If someone steals your encrypted backend data, it's going to be useless without the master key. What we're going to be using here, as you might have seen in the talk description, I referenced the free tier of Google Cloud, but since then they have developed the internal storage mechanism that is consensus-based a little bit more. And so I'm actually going to be giving this talk based on the internal storage mechanism that uses Raft. So how do we initialize a cluster? Well, in this case, we would want to use the CLI to run the Vault operator init command. And in this case, we will be generating 7 shares with a key threshold of 4. Now, what we can do is on each of these 3 Raspberry Pis, we generate a PGP key pair that stays on each unit. And we take the public keys from each of the 3 and take them to where we are initializing the Vault. And so we tell Vault to give us the key shares that are encrypted with these PGP keys. So the first 3 shares are each encrypted with the public key of one of the 3 vaults. One is encrypted with the PGP key on, a personal YubiKey. And then the other three are encrypted with a PGP key that only exists on 2 YubiKeys that are stored elsewhere. These are basically just backup keys. In case something happens to the 3 vaults, we're still able to get into it. And of course, we also can encrypt the root token with a PGP key. And so what this setup does is it allows the 3 other vaults, or the 3 Raspberry Pis, to contribute 3 keys towards unsealing the vault, but it still requires manual intervention. So if you, for some reason, want to manually seal shut a vault, it's not going to end up getting unsealed just by the cron job running that tries to unseal it, for example. There is a transit seal mechanism that can allow you to automatically unseal the vaults, but I actually specifically did not want to do that because I prefer the option of requiring a manual unsealing, but just with 1 key, rather than having to manually bootstrap each individual vault. And so with this setup, we can basically create quasi-hardware security modules. With the combination of Zimkey and Vault, we can have a second vault initialized on each Raspberry Pi that has a local file backend. This vault will have a single share, and that share, the unseal key, will be encrypted with the Zim key, and that's the only thing that will be used to unlock the vault, the secondary vault, but it will only be stored on that particular Pi. And so what this would do is that it would require a quorum to come online to unseal the vault. A single node comes online, the unseal server, so the secondary vault, is automatically unsealed using the unseal share that is encrypted by that local Zim key. The node contacts the other unseal servers to get the unseal key for the primary vault that's stored there, as well as the secondary one that's local. And then the user adds the 4th unseal key to unseal the node, and then the vault server joins the cluster. So what does this look like? I have diagrams because that was a confusing explanation. So we start with the 3 nodes, and I want to make it clear here that the symbol in the middle is representing the abstract concept of the storage backend. In this case, the storage backend actually exists on all 3 of the nodes, but there won't be the consensus happening, and you won't be able to access it on node C until it's actually unsealed. So how do we do this? The unseal vault, so the secondary vault on node C, is unlocked at startup using the single unseal key that was created for that vault. The primary vault gets the first share of its unseal key from the same node. And of course, this would be done using, for example, a Python script with the HVAC library, which I believe stands for HashiCorp Vault something something. It's a Python library that makes it very easy to access Vault. Next, the second share would be gotten from node A, and the third unseal share would be gotten from node B. And again, this is from the unseal vaults that exist on the other 2 nodes. Finally, the 4th key is provided manually by the user, and node C is then unsealed and able to access the storage backend. And so now if you query any of these 3 vaults, since they are operating in a high availability cluster, you'll be able to get the same backend secrets that you'll be able to get from the other 2. What happens if, for example, we have some sort of catastrophe and we have to restore from a backup of the encrypted data that we took from one of the nodes? In that case, we can use the personal share from the personal YubiKey and decrypt the two backup shares using the PGP key on one of the two backup UB keys that are stored in separate locations, for example, a safe deposit box. That can be used to decrypt that backend and start it up on a new node. But of course, we don't want to have insecure communication with the other vaults. So what's our solution here? Well, one of the things that Vault is really great for is that it allows you to easily manage your own little mini certificate authority. Now, I'm not going to go through the actual process of setting this up step by step. The HashiCorp learning software has a great tutorial on this, but the basic summary of the process is creating an air-gapped certificate authority certificate, creating certificates, signing requests for the intermediate certificates that you want to use, sign the CSRs and import them into Vault, and issue these certificates from the intermediate certificate authority that you store in your live Vault cluster. So what advantages does the Internet of Things give us when we create these? Well, for starters, it makes it really easy to create air-gapped devices. For example, if you take a Raspberry Pi Zero, you can be guaranteed that it's never ever going to connect to the internet unless you plug an Ethernet adapter into it, because it has no wireless, technology at all. So if you solder a header onto the Raspberry Pi Zero, and you attach a SIM key, plug in a high endurance micro SD card, and run a unique instance of Vault on there that's not part of the cluster, that just uses the local file backend, you can have an extremely, extremely secure air-gapped devices. One thing, if you want to be super overboard with your security, is to have 3 unseal keys, one that's encrypted by the SIM key, one that's encrypted by your personal YubiKey key, one that's stored on paper in your safe deposit box. And you could even store the SIM key and the Raspberry Pi Zero and the SD card at 3 separate locations, because you need all 3 of those for the SIM key to be able to uncrypt and decrypt anything. And so the certificates we're going to have are going to be a root certificate with a maximum lease TTL of 87,600 hours, which is 10 years. We'll have an intermediate certificate on our live cluster, which has a maximum lease TTL of 42,800 hours, which is 5 years. And we'll have lease certificates with short TTLs, for example, 12 to 48 hours. And this is where mitigating breaches comes in. If someone steals the certificate that we use to access a certain microservice that we're running on our IoT, the possibility of the breach lasting for a long period of time is nil, because they don't have any way to renew the certificate. So we begin by creating the rule that we're going to use to generate these certificates. And from there, we're going to generate individual certificates for each node we want. In this case, we're generating the server certificates for our first vault. I don't know if you guys can hear that. My automatic dog feeder is feeding, so I will wait in case it's making noise, picking up on the microphone. Okay. So after we have our rule and our initial certificate, we can use this to configure the server certificate for Vault A. So we say, our first vault is going to exist at vaulta.local, port 8200, which is the standard port for Vault. And we're going to use the certificate and key files that we just generated. And of course, we're specifying that we want to use the Raft backend storage. And the rest of the configuration is pretty standard for creating a high availability cluster. So this is the server certificate that our clients are going to get when used to encrypt the connection when they're talking to this vault. And if we want to run the unseal vaults, so the vaults that we use just to store the unseal keys for the main vault, we want to have client certificates. For that, we can, again, set up a specific server certificate for those vaults. And we can also require the vault servers to require and verify client certificates. again, that have to be generated by our certificate authority. And so what we would do in that case is when we're connecting using the Vault agent, we just need to specify the client certificate we want to use to authenticate with the Vault server. And this gives our unseal process a little bit of extra security, because no node will be able to get an unseal key to begin with unless it has a signed certificate. So now all of our devices are communicating together. Let's make sure we're not going to leak our SSH keys anymore. Again, this is very easy to set up using one-time SSH passwords. So rather than having to deal with custom configurations for each individual server and having to worry about, getting everything configured that way, we can just have one-time passwords and a single SSH key per machine. What we need to do is we need to enable the Vault secret engine for SSH. We need to create a one-time password rule that will allow us to actually create these tokens. And that's the entirety of the configuration. What we have here in this example is a one-time password actually being created for use with the server at 10.0.0.27. And as you can see, the least duration is 600 seconds. So the one-time password, if it were stolen, is only good for 10 minutes. But we can also automate this using the CLI. So if we say Vault SSH, use the rule with the one-time password tokens, again, say we want to authenticate with one-time passwords. And if we have SSH pass installed, whenever the connection is initiated, we'll automatically enter the one-time password and we'll be connected. So we never have to worry about making sure that the configuration, the actual private key material for the servers that we control are, differentiated and safe and prevent leakage, because we can have just one key per machine and we won't have to worry about actually, having that level of differentiation. The single SSH key uses different one-time passwords every single time we want to connect. The way this works on the back end is that there is a Vault SSH helper library, and that is what's used for client authentication. So whenever you connect to the server, you send in the one-time password, it runs the helper connects to the Vault checks that the password is valid, and then it allows the connection to go through. So this is a very, very simple way to compartmentalize access to our servers. So how can we improve this further? One possibility would be to actually use the Google Cloud backend. This was actually what my original idea was to do. And this is a backend that supports high availability. So if, for example, you needed to have vaults, different vaults with a single backend where the vaults are in different locations and they couldn't easily communicate with each other, you could have the cloud backend, because they actually communicate through the backend once the vault is unsealed. Additionally, we can have improved auditing. The basic auditing method is to just store everything right where the vault is, but we can have it write our audit logs to syslog, and we can store this off-site somewhere or somewhere more secure, or even just in a separate encrypted device that's specifically set up to receive the audit logs. And from there, we can, for example, apply some Elasticsearch log monitoring to it to check for any sort of abnormalities or do whatever auditing we feel is necessary to protect our secrets. So that's the general plan. And if anyone has any questions or feedback, I'll be glad to hear it.